When you think of a machine learning model, you probably picture lines of code, vast datasets, or futuristic algorithms. But what if I told you the core mechanics of AI are governed by physics concepts penned over 300 years ago? Today, we're exploring the surprising parallels between Newton's laws of motion and the engine of modern AI. Artificial intelligence doesn't need to move physical objects, but it does need to overcome inertia, apply force, and constantly react to error. Join us as we break down how the three most foundational laws of classical mechanics map perfectly to the training and behavior of machine learning models. Newton's first law: an object will remain at rest or in uniform motion unless acted upon by a net external force. This is the law of inertia. In machine learning, a model starts training with completely random weights. If we do nothing, the model stays at rest with terrible performance. The learning process must overcome this initial inertia. But more importantly, once a model finds a comfortable, but suboptimal, spot in its learning, it takes a significant force to move it out. This is why the learning rate must be carefully tuned, too small, and it never escapes bad inertia. Newton's second law: force equals mass times acceleration, $F equals ma $. This describes how force creates motion. In milliliter, this is the core of how a model actually learns. The force, $F, in our model is the gradient, the direction and magnitude of the steepest descent on the loss landscape. It tells the model exactly where to go to reduce error. The acceleration, $A, is the amount the model's weights are actually changed. The mass, $M, is our resistance to change, or more specifically, the reciprocal of the learning rate. A high learning rate, low mass, causes high acceleration and fast learning, but it can overshoot the goal. A low learning rate, high mass, learns slowly but precisely. The optimization algorithms, like stochastic gradient descent, (SGD), are the systems we use to calculate and apply this force accurately. Newton's third law: for every action, there is an equal and opposite reaction. This is the principle of interaction. In milliliter training, this is called backpropagation. The action is the model's prediction, which causes an error. This error is the force exerted by the environment on the model. The reaction is the error signal flowing backward through the network. The backpropagation: for every prediction the network makes, the environment instantly pushes back with a reaction, the error signal. This constant, equal, and opposite feedback loop is what allows the network to iteratively correct itself, ensuring that its learning is constantly grounded in the reality of the training data. There's one more physics concept essential to modern AI: momentum. In physics, momentum keeps things moving. In milliliter, we often add a momentum term to our optimizers. This prevents the model from getting stuck in those little, inertial dips and helps it roll over small bumps in the loss landscape, allowing it to efficiently find the deepest valley, the best solution, without getting bogged down. It's Newton's laws, augmented by a little push of accumulated speed. From the law of inertia defining the start of learning, to the force of the gradient driving optimization, to the action-reaction of backpropagation, the very DNA of artificial intelligence is built on the genius of classical physics. It reminds us that at the core of complexity often lies elegant, timeless simplicity. What other classic science concepts do you see hiding in modern tech? Let me know in the comments below. If you found this connection fascinating, like this video, and be sure to subscribe to LogicLab's AI for more deep dives into the science of the future. Thanks for watching, and I'll see you in the next one.